Okay, I guess maybe we can start now. Just 1 second. Okay. So first, I'm going to review the homework, and then the second, I'm going to review exam 2. Okay. So let's. Okay. So last homework is about Morse structure. Okay. Let's see. So the first question in here is we have a Morse capacitor, and silicon is doped with Nd. Okay, so which means this is the N type, right? And then asking the in here question is calculate the surface potential required to make the semiconductor interface. First, intrinsic, second, strong inversion. Okay. So before answering this question, you have to conceptually understand the the first question is in the surface potential in the silicon, we want to make the in here is a semiconductor surface intrinsic. So initially, semiconductor is n-type, which means that we have a large number of electrons exist. Okay. To make the surface intrinsic, in the metal, we have to apply the negative voltage. Okay, so we apply the negative voltage so that the electron is pushing away from the surface. Okay, and then if so for this one is, as you can see, if you do this one is we have a condition like Ni exponential minus Ei kt, and this one equals Md, right? So if we calculate this one, Ef minus Ei over kt, this value will be around 0.4 volt, okay? But as you can see, is that for this structure, we need to apply the negative potential, okay, to make the intrinsic. So the final answer for this surface potential for the A case, we need to apply the negative 0.4 volt. Okay? And then now, if we keep increasing the negative voltage in here, we're going to further push away the electron so that initially it creates a depletion and then reach to the intrinsic, and then finally we reach to the strong inversion. So strong inversion condition is surface potential magnitude is 2 times of the potential difference between the Fermi and then the intrinsic energy level. So that follows this condition. And again, is that for final answer, this one is negative 2 times this value, right? So this one is negative 0.8 volt. We need to apply to create a strong inversion. Okay? So that is the first question in here. The second question is replace the table in the textbook is 12.1 for the case of N substrate MOS capacitor. Okay, so again, as I think about, N type is majority carrier going to be electron. Okay, and then we apply the different bias in the metal, and then we look at the surface potential. Okay, so in here is that when you apply the, for example, positive voltage. Okay, so again, let's just draw briefly. So metal, oxide, and then this is N silicon. You have lots of electron. So when you apply the positive voltage in the metal, so then in the semiconductor side surface going to be positive, right? And then the magnitude of this potential going to be larger than 0 in here. And then because we apply the positive in the metal, so electron is attracted to the interface to create the accumulation. Okay. So when you look at the carrier density for this case, surface charge, this one going to be more than the doping concentration. Okay. That's the condition for the positive. Now, if you change this metal VG potential negative, so when you apply the negative, this one, now electron is pushing away, right? So that in the semiconductor side, you're going to start to create a depletion. Okay. And then if you look at the magnitude, the surface potential still is less than the potential difference between the Fermi energy level and the intrinsic energy level in this case. Okay, so magnitude is smaller than this, but again, its surface potential, the sign itself is negative. Okay, for this condition, you're going to have a surface this charge going to follow this relationship. Okay, because in here is still is electron is dominant. Okay, in the surface, but their magnitude is smaller than the doping concentration, right? Because it's depleted. Now we're going to further increase the negative potential in the metal. Okay, then at some point now is the magnitude of surface potential going to be equal to the magnitude of this potential difference between the Fermi and the intrinsic energy level. Okay. For this condition is now, as you know, is the surface condition going to be intrinsic, which means your electron, hole, concentration going to be equal to the intrinsic carrier concentration. Okay? So that is the this condition. If you further increase the negative potential, then now is at some point surface potential is going to be larger than your magnitude of your potential difference in here. Okay. So for this condition is that the surface condition is now changed to the inversion. So which means that now hole concentration, okay, hole concentration is much larger than the electron concentration. Okay. And then in here is we create the inversion. Okay. Now, if we further increase this one, is at some point we're going to have condition of that this surface potential magnitude going to be equal to 2 times of this potential difference. Okay. At that point is that we name in our class is that that's the onset of strong inversion, and then that's the strong inversion condition. Okay. And then for this case is hole concentration is equal to your original is ND doping. Okay. And then finally, if you further increase, then you have a strong inversion. And then in here is a hole concentration. This one is larger than your doping concentration. Okay. So that way is we can replace the table further N-type substrate. Okay. Okay. And then 12.14. Okay. This one is we have ideal Morse diode, and then doping is Na. Okay, so which means that this is a P-type silicon. Okay, and then we have oxide thickness is given 120 angstrom, which means that this is a 12 nanometer. Okay. So for this condition is that calculate the value of minimum capacitance on the CV curve. Okay. So in the semiconductor, as we discussed, we have oxide, and then we have silicon. So in here is a P silicon, and then we have metal. Right. So when you have this kind of structure, and then when you apply the bias, we will have the capacitance first across the oxide, that is typically COX we put, and then below the semiconductor you have another is the capacitance. Okay. And then typically this one is coming from the junction capacitance in the semiconductor. Okay. So from these two capacitance, because capacitance in this case, as you can see, is connected in series. So total capacitance you calculate is that 1 over COX plus 1 over this junction capacitance. Okay. And then typically this junction capacitance you can calculate from the epsilon A over W from in here, you can calculate. Okay. And then if this dimension is all same in here in the A, we can actually later on is we can rewrite this one in terms of the unit capacitance. And here we can calculate. Okay, so from this equation we can calculate the total capacitance. So minimum capacitance happens when the W going into the W max. So from there, if you calculate this one, C minimum COX plus, we have this one. Now from in here is that if we replace this one, then in this case is that C minimum plus COX, and then this term is going in here. Okay, so now is that we just follow the calculation in here. So epsilon in the semiconductor, we're gonna put this one is over there. We put, so that's the given number. COX is we can calculate from the epsilon of the oxide, and then the thickness of in here. So similar to this equation, epsilon D is that in here is that 12 nanometer we put. Okay, and then the epsilon, this one is epsilon R plus R multiply epsilon 0. Okay, so oxide epsilon R is around 3.9. Okay, epsilon 0 is the same way, is in the vacuum epsilon 0 is we can use 8.85 times 10 to minus 14. So using that one is we can calculate this COX in here. The W, this one, is when they reach to the W max, which means that the potential, okay, so when the potential, this one is 2 times of the potential difference as we calculate in the previous the example. So from there is if we follow that number, then W depletion width we can also calculate in here. Okay, so combine this all the calculation, plug in here, we can obtain this C minimum for this question. Okay. Okay. And then 13.2. Okay. This one, in fact, we discussed in the class. So N-channel MOS FET or N-channel MOS structure in here. Okay. When the gate and the drain is connected together, as you know, is drain voltage equal to gate voltage, right? The condition we have. And then if we have this condition, now we're going to have this kind of condition. Drain T, we have this condition. The reason is NMOS case, VT, this one is positive. So this configuration, when you connect the gate to the drain, that always satisfy this relationship in here. Okay, so for this relationship, tell us that now is regional operation of this device is going to be saturation. Okay, so that is the first this one. So at the saturation is that if you look at the drain current versus the drain voltage, the current versus voltage characteristic. So let's say this is a drain voltage, okay? And then this is the drain current in here. If you plot this one at the saturation, we're gonna see that the curve is something like this. It's a little bit parabolic. And then this on start happens in the VT. Okay, so it followed this kind of drain versus voltage characteristic. Okay, so that will be answer for this question. Okay, so that way is that we're gonna end for the homework. And then next one is the exam is exam 2. Okay. So the first question for the exam is we are looking at BJT n plus P and BJT. Okay. And then their relative doping is given in here. So emitter is 10 to 17, base 10 to 16, collector is 10 to 15. Okay. And then the first question is asking about at the equilibrium, show the energy band diagram for this BJT. Okay. So as you know, at the equilibrium, our first condition should be EF should be constant throughout the structure. Okay. And then the relative doping represent how close is this EF related to their conduction band or valence band. Okay. So the first emitter side is M plus, means that the EF is close to the EC, right? And then this magnitude is much smallest compared to the other one. So for the, especially is N-type, this is a collector side. If we look at the collector side is that now if we draw the same AEC, then you have this kind of difference, okay? And then is base side is that is a P-type semiconductor. So which means in here, base is that now is EV is close to the EF. Okay. Now this magnitude is between this emitter side, this relative difference, and then collector side relative difference between these two values. Okay, so this is a middle value. Okay, now for in here is that if we draw same way, so relatively you're gonna get something like this. Okay, so this represent equilibrium energy band diagram for this BJT. Okay, and then key point in here is that their doping is different, so you have to consider this doping. Okay. And then second question is calculate the majority carrier and minority carrier concentration, okay, at the depletion edge of the emitter. Okay. So this question is emitter is we calculate the majority carrier and minority carrier. So to answer this one, we need to look at the emitter side. Emitter side is N plus doped. Okay. So you have to clearly mention to answer this question, N plus emitter, so which means that the majority carrier going to be electron. Okay. And then minority carrier going to be hole. Okay. So that is the first step. You need to identify which one going to be majority carrier and minority carrier based on the doping of this emitter side. Okay. Now, anti-majority carrier, when you apply the bias in here, is that the number of this electron is going to be similar to the original doping concentration. So, which means that this one is 10 to 17, right? So that number going to be majority carrier concentration. Okay. Minority carrier concentration is follow that thermal equilibrium. This concentration multiply exponential is in here is applied bias 0.5 volt divided by kT. Okay, kT over Q, 9 volt, right? And then the PON at the thermal equilibrium is, as you know, this is going to be 10 to 3. Okay. So following this equation, we can calculate the number of this minority carrier concentration. Okay. So that will be answer for the question B. Question C is we define is this alpha value in here, okay? And then the alpha value in here is in the active mode is larger than in the reverse active mode, okay? Explain the reason in here, okay? So for answer this one is, as you can see, is we have the transistor, okay, which has the emitter side is highly doped. Okay, so due to this region is that when you look at the alpha value in the active mode or inverse active mode, we can see that in the active mode, this alpha value is much larger than the inverse active mode. Okay, so to answer this one, you need to mention about the doping of the emitter side is much higher than the collector side. And then D is when transistor operate in the saturation. Okay, when you look at the collector current is in fact is decreased. Okay, to answer this one, saturation region, as you know, emitter and base and collector and base, both of them are forward bias. Okay, so which means that when the forward bias is applied in the post junction, then your current is that the IE current and the IC current is their opposite direction. So which means that when you look at the total current is actually decreased by this forward biased IC current in here. Okay, so you have to mention that kind of thing in here.
Wait, Professor, could you repeat that explanation?
Okay, so in the saturation region, right? In the saturation region is, if you look at the transistor, so you have emitter, base, and collector. So when you apply the forward bias, emitter and base, you have majority carrier current is flow to the collector, right? And then when the saturation is again, you're going to have forward bias. So the current is in the forward bias majority carrier from the collector side is in the opposite direction. So when you look at the total, this collector current is actually decreased due to this opposite direction of the current from the collector and base. Okay?
Okay, yeah, thank you.
Yeah.
Sir.
Yes.
If we have the inverse active mode, the flow of carriers are gonna decrease, right? The flow
Inverse,
yes.
Inverse active mode is compared to the active mode, right?
Yes.
So for that case, the doping is in here is smaller than the emitter side. So which means that the amount of majority carrier is close to this base and collector is smaller. So the current is smaller, right?
So the flow of carriers are gonna decrease when we apply the inverse active mode, right? Because we have less doping.
Right, we have less dope, so that's the related with actually this one.
Yeah, because I said my answer was that the flow of carriers it decreases. I didn't mention because of the doping, but like I assume it was understood. But I got no credit, so I don't know.
Maybe after class, I'll look at your answer again.
Right.
Okay? Yeah, I cannot answer right now, but later on, certainly. Okay, that's good. Okay, and then the E question. This one is just looking at the general response of this BJT. Okay, so when the BJT, the temperature is going up, how this temperature affect the transistor. Okay, so in the class, we discussed about this temperature effect. In fact, this temperature effect affect two parameters in a different way. One is carrier lifetime, another one is mobility. Okay. The carrier lifetime is actually when the temperature is increased, and then eventually this one increased the gain of this beta. Okay. The mobility is actually decreased, and this one is decreased this the beta. But the overall, as we discussed, overall dominant factor is that this top portion. So eventually, when the temperature is increased, we see the beta is increased. So this factor IC going to be increased. So that's the answer for this question. So and then I'm looking for those discussions. Okay. Okay. F and the G, this one is kind of related with our homework question. Okay. So as you remember, if you look at this one, is a homework, we have similar this question. Okay. So I'm looking for that you're going to actually, from that question, you can answer this one. So if you look at this one, the BJT is operate in the active region. Okay, so active region means we have emitter, base, and collector. Emitter and base is that the forward bias, and then the base and collector is we apply the reverse bias. Okay, and the initial condition is that the forward bias is we fix emitter and base. And then reverse bias is base and collector was the 5 volt. Okay. Okay. For this condition is let's say effective base width is that is the 1 micrometer. Okay. Now, as we discuss in here is that when we increase the base and collector reverse bias, the magnitude. And as you know, is this one effectively increase the depletion width between the base and collector, so that effectively that reduced this base width. Okay, and then when this one happened, is we know that the collector current is increased. So as similar to in the our homework, if you relate to this one, is that let's say collector current initial, and then the new collector current, the ratio this one will follow that the base width initial, base width new. Okay. So, and then in here is new collector current is a 20% increase. So which means that this one is 1.2 IC1. Okay. And then initial WP1 was 1 micrometer. Okay. So if we have the calculation, this one, WB2, right? WB2 is, we can calculate 1 micrometer divided 1.2, right? So from there is we can have the new WB1 require this 20% increase in the collector current. Okay. Now, how WB1 is related with this structure? In this case, as you can see, the effective base width is WB effective. This one related with depletion change in the base and collector. Okay, and then this change is related with in the base side. Okay, in the base side is that the depletion width change. So in our case, is base is p-type. Okay, and then the base width depletion width change, we have formula related with your applied bias. Okay, so if we use this formula, now is we can see how much this XP need to be changed to compensate this one. So you can see is initially base width. This is a change of your XP. Okay. So then from in here is that you can actually calculate the is VBC, right? So that way is that you can calculate this required is VBC. Okay, so that is the first question in here. Okay, and then second question in here is this is also similar to our homework question. The relationship between the current, okay, with the early voltage we have this kind of relationship, right? So this relationship, as remember, we have a graph. This is the, and this is the IC, and then with the early voltage, as you know, if we define the early voltage in this point, okay, the change of this one is related with this kind of curve, right? So we can formulate this ratio. Now, it's the same way, it's 20%. change. This one is 1.2 C1. Okay. So we have this relationship, and then from there is that initially this one is 5 volt. Okay. And then from the one, you have change of this VC 2. So if we relate that one, yes, we can obtain this VA. So that way you answer this question. Okay, so that is the first question. And second question is starting with the IV characteristic of gallium arsenide JFET. Okay. So for this one is if you look at the current versus the voltage characteristic in here is that initially when there is no bias in the metal applied, okay, there's no bias applied is the current flow in this level. Okay, so which means that for this structure, as you remember, is we draw this way. So this is the channel in the gate. Let's say this is the drain side and this is the source. So let's just ground it in here. Okay. And then you have the gate voltage is applied. Okay. And then between the gate and the channel, you use the junction, PN junction, right? Okay. Now, in here is that as you can see, as we apply the more negative voltage, okay, more negative voltage, current is decreasing. So which means that the depletion in here is that increased. Okay. So which means that in here is that to apply the more negative voltage, okay, to create the depletion is larger and larger. Okay. You need to have the in here is the channel should be N, right? So that will answer this channel should be N channel. Okay. And then the second one in here is, if you look at the output characteristic in here is the after JFET reach to the saturation, the current in here is relatively flat. Okay, it doesn't change. So which means that when you look at the length of this channel, okay, this length of channel after saturation does not affect the current, saturation current. As we discussed, when the device is reached to the saturation, in the drain side, you're going to start to have the pinch up. Okay. And then when the drain voltage is further increased, the pinch up point is moving toward this source side. Okay. Now, if the channel L is very small, to see this effective change of this pinch up point moving toward the source side, then now we're gonna start to see that this ID current is increased. Okay. So, but for this output characteristic, if you look at in here, we do not see this kind of change in the ID current, which means that the effect of this pinch up point moving toward the source side is going to be minimal. So that's the case for the long channel this device. Okay, so correct answer for this one is B, going to long channel and then the region going to be from this explanation. And then question C, this is also is a general question related with all FET device. Okay, so once this JFET reaches to the pinch-off, okay, and the drain current is now reached to the saturation. Okay, and then in fact in the structure is, as you can see, once the channel is reached to the pinch-off, the channel is effectively in the drawing is disappear in the structure. Okay, but still, as you can see, the current is remain as the constant, and then we see the drain current flow through the channel. Okay, the reason for this one is when you look at when device reaches the pinch-off, and then when you look at the electric field direction in this depletion region, the field this direction align such a way that, for example, in the N-channel device, electron is swept to this drain side. Okay? So that's the reason is that we can still see this current flow through this structure after device reached the pinch-off. Okay? So that kind of discussion will answer this question in here. Okay. Question D, this one is when we discuss about JFET, we discuss about the frequency response of the device. Okay, and then the frequency response of the device, this one related with the channel length and also the doping and also mobility of this material in channel. Okay, so when we decrease the channel length, we can increase the FT value. When you increase the doping, again, we can increase the FT value. When you also choose the material which has the higher mobility, then we can also improve this channel, the FT value. Okay, so some kind of that kind of discussion will answer this question in here. Okay, and then the question 3, this one is, now we have the metal and then N-type silicon form the Schottky diode. Okay, and then the experimental capacitance when we measure for this Schottky diode, it follows this equation in here. Okay. So for this condition, is now is the question we asking in here is first in the A, what is the VBI? Okay. So to answer this question is as we discussed in the class, you have to look at the relationship between the capacitance and then the your bias. Okay. So we have this kind of relationship is VBI minus your applied voltage related with Q, epsilon, and D, and area. Okay. So we have to start with this relationship in here. So to calculate the VBI, simply as you can see, this value is when you change the VA, okay? When the VA close to the VBI, this value going to be 0. Okay? So that applied bias related with a VBI for this structure. So if you do VBI in here is, as you can see, 0.5 volt. Okay? So that will answer the first question. And then the second question is, now we are asking about the doping concentration in the structure. So to answer this doping concentration is we need to start with the relationship, as I mentioned. So this one is 2 times VBI, okay, minus VA. And then in here is a Q epsilon NA and the A. Okay. So if you look at this one, now is in here, you have to also is carefully correlate the unit. And here is unit of the microfarad in the capacitance. So micro is 10 to minus 6. Okay. So you need to correlate this one. And then you can correlate this one too. Okay. So VBI is that we already calculate is 1. So you can have the times Q epsilon and D multiply area, cross-sectional area, okay, multiply VBI. This one is 1 times 10 to 5, okay? So VBI is calculated, we already obtained from the A, right? And then the Q is that is a material parameter. Epsilon silicon is also material parameter, so it's given in here. Okay, the area, this one is given in here, right? So if you correlate this one, now is from that calculation, you can obtain this is ND. You can calculate that is a doping concentration of the silicon. Okay, so using that relationship is that you can calculate that is doping. And then the C question is asking about the Schottky barrier height. Okay, okay. Schottky barrier height is we calculate from the you have the is a metal work function, right? So metal work function, you have this one, okay. And then you have a semiconductor work function, right? From in here is that you can calculate this the barrier height. Okay. And then the semiconductor work function, this one is we can calculate is, as you know, is this one related with Q electron affinity, okay, and then plus the potential difference between the EC minus EF. That gave us that this semiconductor work function, okay, and then that we can calculate in here. This value is again, as you remember, that's one related with KT over Q at N and C and D. Okay. For the silicon, the NC is given this value. Okay, so using this one is that you can calculate the this Schottky barrier height. Okay. Okay. So that way is you can calculate. And then as I mentioned, metal work function, this one is related, is from the relationship is IV. You can calculate this metal work function. Okay. And then question E is, let's say this is also similar to our homework. If there is no space charge created in the N-type silicon case, okay, what is the required doping concentration for this semiconductor? So this one is, as you know, is that to have this condition, the metal work function equals your semiconductor work function. Okay. So for this condition, you will not have the space charge region or depletion region in the semiconductor. Okay. So for this case is that now is that you can have the required metal work function. Okay. And then semiconductor, this work function related with is the electron affinity plus the same way is that EC minus EF, this difference, potential difference. Okay. So to correlate this equation, you can have the required this value of this EC minus EF. Okay. That will give us the now is doping concentration following the KT over Q. It's the same way, and C over ND, right? So that will answer this question in here. And then F, this one is Schottky barrier diode is much faster in switching than the PN diode, as we discussed in the class. The reason for this one is Schottky barrier diode. This one is based on the majority carrier device. Okay, PN junction diode is again, you can always consider majority carrier and then minority carrier. Okay. Since the Schottky barrier diode is related with the majority carrier, only majority carrier, there is no storage capacitance created in the Schottky barrier diode. Okay. So that's the reason is that the switching characteristic for the Schottky barrier diode is much faster. And also is in the class, we related with that kind of characteristic is when you apply the current, is Schottky barrier is right away is increased like this. But the PN, there is some delay. Time delay happens due to the storage capacitance. Okay, so if you answer with those discussion, that will answer this question in here. Okay, so that is the exam number 2. Okay. So overall is I think yeah, that is the overall for the exam and then the homeworks. And we have 15 minutes left. So if you have any question, maybe I will answer your questions. Okay, yeah, Barry. Oh, so is I would say is that let's say 70% are going to be whatever we covered after second exam, okay? And then still, as you know, is all these PN junction, everything, they are all related. So I would say 30% still covered in the previous chapters. Okay. Okay. So that way.
Professor,
Oh, okay, Carlos.
no, I was just gonna say that I'd like to have a discussion with you about my exam, if that's possible. Like we can talk in private, like after the class.
Yeah, after the class, maybe. I think this time it's still. Other thing is that for the final, as I mentioned, is that we're gonna follow the schedule is provided in the school. Okay, so we'll follow that schedule. One thing is that this time is that I'm gonna send you the Zoom link by email. Okay, so instead of using the Blackboard, is I like to have all of us join into the Zoom, and then having the exam. Okay, so I will send you the link later on. Okay, and then now is for the final. You can have this formula sheet allowed. Okay, and then I'm hoping at least it's a 10 minutes before the exam. You're gonna all join into this Zoom link, okay? And then turn on your camera, and then I want to see that everyone ready for the exam, okay? Then exact time, the exam time, I'm gonna send you the same way. It's the exam by email, okay? So the detailed direction still is I'm gonna send you by email, okay? So that will cover the final exam. And then the final grade, as I mentioned, is I'm going to curve. So which means that later on is I calculate all the performance of your exam, homework, and everything. And then if you are in the middle of the class, you expect a B grade. And then from there is that your grade going to be changing. It's going up and going down. Okay. That is the and oh yeah, can you say? Then you expect a B grade. Okay. So the grade, the final grade is that your average is 50, right? So there is some range I'm going to set based on the result and curve, and then you expect that this is the falling into the B grade. Okay, and then from there is you go up, going down. Okay.
Professor, the exam gonna be like 2 hours?
Exam will be following the exact hours is provided in the school. I think it's 2 hours, right? Final exam. Okay. Yes, 2 hours. Yeah.
And we're gonna start at 11?
Let me check our final. Have you checked our final exam? When is the date? Is
Professor, I think the date is Thursday.
I think it's start at 10:30.
Is 17th? Is it 17th?
Yes. Yes.
What time is it start?
Professor, it's from 10:30 to 12:45 p.m.
Okay. Then yes, we're gonna follow that schedule. Okay. And then still is you have to consider it's the same way I'm going to apply is you need to later on after you finish the exam, you need to submit by email. Okay. So you have to consider your time, right? Based on that duration. Okay. Anything else do you have? Okay. So anyway, is that this way is we're gonna end our class for this semester, and also still is before exam is I'm available. So if you have any question, you can send an email. So I will answer your question by email. And I think that's all from my side. So thank you very much for the class, and hopefully everyone's safe and then having the good winter. Okay. Any other questions do you have? Okay. If you do not have any other question, then can we end our class?
Yeah, thank you, Professor. Have a good
Okay.
day.
Thank you very much.
Thank you,
Okay.
Professor. Have a good
Okay.
winter break.
Thank you.
Professor, you will be available on the email, right?
Yes, you can send the email. So I'm available through the email. Okay.
I have some question regarding the exam. So
Okay. Yeah. Sure. It's yeah. Send the email. And also I noticed that Carlos also has the questions. So send the email to me. So I will answer. Yeah.
Okay.
Professor, I was wondering if I could stay after the class leaves.
Okay. Yeah. That's fine. It's I'll be in the class right now in the Zoom. So yeah.
Thank
So maybe let's wait until everyone leaves. Then yeah.
Professor, I also have a question regarding the exam. So
Okay.
can I leave right now so you can talk to Carlos and maybe come back around like 12:20 or something?
In fact, is that I only sign up the certain period in this Blackboard. So I think best way is that can we reschedule by email the time?
Yes, so I will send you an email then.
Yeah, then maybe probably I'm gonna send you Zoom link, right?
Okay,
So,
thank you.
yeah. Okay, that's good. Okay. Okay, Carlos, I think we can discuss. Let me open your exam.
All right, thank you.
Just 1 second.